So section 2 goes the other way with the natural log. We are now going to integrate it. So we learn how to take the derivative. The derivative of 1 over x is the natural log of x. So it stands to reason that if I integrate, the derivative of natural log of x is 1 over x. Is that what I said? Or did I say that backwards? Okay, so I'm already thinking, I'm in this mode here. If I integrate 1 over x, I get the natural log of x going the other way. It makes sense. But there's something that we have to include, the absolute value symbols. Why? Yeah, the natural log of something has to be positive. And we have to include the plus c. As usual, there's no faster way to get a problem wrong than to forget the plus c. So here's your log rule for integration in 3 different forms. We have the integral of 1 over x dx is the natural log of the absolute value of x plus c. The chain rule looking version of that would be the integral of 1 over u du is equal to the natural log of the absolute value of u plus c, which makes it really nice. And if we rewrite this one in a different format using the du equals u prime dx differential form that we've been using for integration, then we can rewrite this form as this form, and this form is the one that we're going to use most of the time. The integral of u prime over u dx equals the natural log of the absolute value of u plus c. You get the same result here and here. So let's take a look at how that's written, and remember the absolute value in the integral after you take the integral is absolutely necessary because of the fact that we can't take the natural log of a negative number. So we have to include them. But what do you notice about the way that this one right here is written? Like in terms of patterns. So basically, if I'm looking for a pattern and I'm integrating, if I see the derivative of the denominator in the numerator, then I can use the log rule for integration. And it becomes a very easy integral to do. You just have to recognize that pattern. All right, 3 examples. We are integrating 2 over x dx. Yes, if we bring the 2 out, then we have 2 integral 1 over x dx. That's the pattern, u prime over u, basically. The derivative of the denominator is 1, which is the numerator. So therefore, I get what? We are integrating, so we need to say plus c here. You already know how to find c. If you're given some sort of information about the original function, then you can find c. How about this one? Yeah, you need a fancy one here. If there was a 4 up top, then I would have the derivative of the denominator sitting in the numerator. But I can't do that unless I keep this thing unchanged. So 1/4 out front then gives me the pattern here. So when I integrate, what do I get? And you're done. How about the last one? We need a 2 up top because the derivative of x squared plus 1 is 2x. Now we have 2x. 1/2 out front. So my integral is here's your answer. So it's pattern recognition again. And that's the log rule for integration. It's very nice to know. So now that we know that, we can handle functions that look like this if we're trying to find the area under the curve. So it says find the area of the region bounded by the graph of this function. So it would be f of x equals x over x squared plus 1. That's this guy right here. The y-axis in the line x equals 3. So this function, the y-axis and the line x equals 3. And they're not saying the x-axis as well, but when we're finding area, we're kind of implying that we're also including the x-axis. So this is the piece that we're trying to find the area of. Down the road, we're going to do more with that area than just find the area of it. It's like the best chapter ever. It's also the last chapter for calculus. Huh? No. So that's it's coming though. We're closer than you think to the end. So we're getting close. All right, we want to find that area. To do that, what do we need to do? Okay. Huh? From 0 to 3 of the function. Now what? Yeah. Notice that we almost have the derivative of the denominator sitting in the numerator. All I need is a 2. And a 1/2 out front to keep the thing unchanged. Now I can use the log rule for integration. And what do I get?
1/2
absolute value of x squared plus 1. 0 to 3. Okay, now, interesting side note here. Because of the fact that we have the absolute value sitting here, we're guaranteeing that we're positive, right? But with this x squared sitting here, plus 1, will I ever be negative? No. So with a little bit of analysis there, you can switch the absolute value to just parentheses. I will do that. The book will do that. You'll be expected to do that. So you have to think a little bit, do I actually need the absolute value there? In this case, no. So I don't have to worry about the absolute value now when I evaluate this. All right, we're going from 0 to 3. So what do I do? Plug 3 in, so I have the 1/2. Is that out front, or is that still attached, or does it matter?
That is out front.
Does it matter?
Yeah.
No, it doesn't. It's a 1/2 that I can pull out. I can factor that out, or leave it in. Doesn't make any difference. So 1/2 times what?
Natural log of 3 squared is 9 plus 1. Minus natural log of 1.
Now what?
We can use the properties of natural logs to see that we have the natural log of 10 divided by 1.
Interesting. Is that true? Wow, yeah, I guess we should probably use a calculator. So the exact answer you're saying would be 1/2 natural log of 10. Okay, but if we want a decimal approximation, then we plug it into our calculator. So you're all right. The absolute value, no, sorry. The 1/2 natural log 10 is the exact answer, or plug it into your calculator, and what do you get? 1.1513, so 1.151 if we're rounding to 3 decimal places, which is what's preferred, okay? Now, save decimal approximations until the very last possible step. That way you're only rounding once. If you only round once, then you will probably get the right answer in the end. If this was some sort of free response problem and you rounded more than once and you were off here by even 1/1000th in the wrong direction, you will not get credit for the answer. So don't do anything with the calculator until the very last possible moment. Okay? All right, this is the answer, by the way. Either one of these. It doesn't specifically say which one we want, so you can go with the decimal answer if that's appropriate. But getting to this point right here is critically important. More fun examples. This one's already done?
Well, the patterns, like
Yeah, just
Correct. The derivative of the denominator is 3x squared plus 1, exactly what we have here. So, do I need to include absolute value on that?
yeah.
I do. Because if I cube something, that doesn't take away the negative. Plus I have this plus x sitting here. So if we had a negative number, we could wind up negative, and that's not good. How about the next one? What is the derivative of tangent x? Secant squared. So this one's already done too. What do we get? That's right. So we're including absolute value there as well. How about the next one? We need a 2 up top? Just a 2? If I put a 2 up top, then what? But what happened to this? Okay, thanks. Now I can send the 2 in, and I get 2x plus 2, which is the derivative of that. Thanks. What's our answer? Do I need absolute value there? No matter what I plug in for the x squared, it's going to wind up positive, but that's not true over on that one. So we still have to include the absolute value. We can't guarantee that it's going to be positive. How about this one? Okay.